In the previous video we were looking at Coulomb's law that describes the force that exists between two charged particles. In this video we're going to sort of make it a little bit more abstract and deal with electric fields. Now a field is a general construct that is used in physics, and we can describe it as being a region where every point in that region the points are going to experience some sort of force. And the different types of fields describe what is actually causing that force, and so you can sort of fairly obviously determine then that an electric field is going to be due to charges. One of the other fields that we'll come across as we go through this course is a gravitational field. In the gravitational field, the force is due to mass, but in an electric field, the force is due to charges. Now, in a field, it's going to be used to represent that force, and so in an electric field, it's going to show the direction of force that would act on a small positive test charge if the charge was placed in that region. So we're using this idea of a small positive test charge as being the sort of the underlying constraint that we know applies to the field. So if instead we're using a negative charge, we know that the direction of the force would be in the opposite direction. But for an electric field, it's always about a small positive test charge. And that means then if we look at one situation where, let's say we've got a positive charge positioned here, so that's our charge Q. If we were to look at a point, say, in this region, if we were to place a small positive test charge there, two positives, so it's going to be a repulsion, so the force would cause that small positive test charge to be pushed away. If we do that in a different spot, say over here somewhere, then we'd have that the force would push that small positive test charge in that direction. So we can go through that process and sort of map the entire region around that charge, and what we would see is that everywhere the force is going to be pushing that small positive test charge away from charge Q. So the field lines would then look like this. So each of these field lines being directed away from the charge Q, and they're all straight lines because the force is always going to be directed away from charge Q. If, on the other hand, we had a negative charge, so this is not, imagine that these are two very separated charges, small positive test charge is always going to be attracted to that negative charge, and so the field will always be directed towards that negative charge. So these arrows that I'm drawing here, you can see are all directed towards the negative. So in both cases, the field lines are straight. In the case of a positive charge, the field lines are directed away from it. In the case of a negative charge, the field lines are directed towards it. To make it really clear, we'll just notate some aspects about that. So the arrows show the direction of the field at any point in that region. You'll notice that as the arrows get further away from the charge, the spacing of those arrows gets further apart, and that's the second thing that's useful here. The spacing of the field lines tells us something about the strength of the field. And I'll go back up to that diagram and explain that in a bit more detail. So that represents the strength of the field. So if we have a look at, just look at that positive charge again. On the left hand side, if we were to look at a point that was positioned here somewhere, so obviously the field's going to be directed away at that point, But at that point, the field lines in that region are fairly closely spaced together. So if we look at how far apart they are in that sort of, in an arc sort of direction, Whereas if we look at a point further out, let's call this point A closer in and point B further out, at point B those field lines are much further apart, and so the strength of the field at A is much greater than the strength of the field at point B. Now there are a couple of other fairly critical things about field lines that we need to be aware of. The first is that field lines never cross. And the reason for that is that if they were to cross, that would mean then that you'd have a point in space where the force could be either one direction or another, which just doesn't make any sense in physics. If we instead had two fields in a given region, as in if we had two charges each producing an electric field, that means that we need to add those two fields together. So the resultant field will just be the vector addition of those two fields. And you would need to go through and look at every point in that region. So again, as a quick example, we've already seen that for a positive charge, it has a electric field that's directed away from it. If we then had two positive charges, imagine again that we're looking at some point located, let's pick a random point over here somewhere. We know that the field from charge QA, so let's notate that as QA and this is QB. The field from QA will be directed away from that charge. The field from QB will likewise be directed away, but because it's a little bit closer to QB, it's going to be a little bit stronger. So there's the two components of the two electric fields, and so we would add those two together. We would find that the field would be in that sort of direction at that point. So notice that it's not to the left, it's not to the right, it's more directed upwards. And we can go through and then map every single point in this region, and what we would find is that on the extremities, it's still very much going to look the same because they're always being repelled from both positive charges. But through the middle, we get a very different sort of shape about the field, and it would look something like this. Now, this is just a rough sketch, so it hasn't been drawn to scale necessarily, but the shape of the field lines is particularly important to have a look at. So you can see that the field lines are a little bit more of a curved nature as they're in this middle region, and then towards the outside it starts to resemble just that the normal sort of shape because the effect of the other charge is much weaker. So that's the vector addition of two electric fields in a given region due to two different charges. You might want to have a look at what the field would look like if you had a positive charge and a negative charge. Have a go at that and see if you can sketch what that field would look like. We can use one of the PhET apps to have a look at that in more detail in class. So electric field lines don't cross. The next important thing to note is that electric field lines will intersect a metal at 90 degrees. Or a conductor, it might be a better way to put it. And that's because the charge that's on a conductor is distributed in such a way that the field lines will just always be 90 degrees. The specific case we're going to look at is a sphere. And the reason for looking at a sphere is that it's the charge will be evenly distributed across the sphere. So if I can draw a circle well enough to represent that sphere, again let's deal with it being a positive charge, so the positives are going to be distributed on the surface of the sphere. That's because they're all going to be equally repelling each other and are going to try and get as far apart as they can, and so we'd have the charges evenly distributed on the surface of the sphere. And if we went through that process again of mapping out the field at every single point around the sphere, what we would find is that the field lines look very similar to what happens with a small positive charge. So for a sphere outside, it has that same sort of shape, all of the field lines directed away. But if we were to map what would happen on the inside, we'd actually find that all of those components would cancel. So inside the sphere, there is no field. But outside, it resembles a radial field, so that idea of the field lines being directed away. It's a radial field centered on the center of the sphere. So basically, if you were to imagine that all of that charge was concentrated in the middle, then it would look very similarly to the field that we had drawn before. I used the word there that needs a little bit more explanation, and we're just going to have a look very briefly now at the two types of field that you need to be aware of. One is a radial field, and as we said, the ones that we've already drawn there, they consist of straight lines with a common central point. So whenever we're talking about a radial field, they're always directed either away or towards that common central point. And the other one that's particularly important to note is a uniform field. Now, in a uniform field, the field lines are parallel, and they are evenly spaced. So if they're evenly spaced, that means that the strength of the field is constant the whole way through the field. So we've already seen some radial fields. We'll just quickly sketch what a uniform field looks like. And it would be something like if we had two parallel plates that were charged. So let's imagine we've got negative charges on the top, positive charges on the bottom. Then the field that would be produced there would be directed from the positive plate to the negative plate. The field lines would be evenly spaced and they would be parallel. Now, to take this just a little bit further, what you would find around the edge of the plate is that the field lines do actually start to bend, but in between the two plates, the field's going to be a uniform field where the field lines are equally spaced and parallel. Now, the last thing in looking at electric fields is to look at the electric field strength. We're going to do that by considering two charges, and Q1 we're going to call capital Q, and Q2 is going to be lowercase q. And we know then from Coulomb's law the force between those two charges is given by KQQ on R squared. Now, if we consider that this charge here, Q2, if we treat that as our small positive test charge, so that Q is very small, what we can then do is divide by that value of Q. So F over Q is then equal to KQ on R squared. Now that idea of F over Q, that is the force per unit charge. So the force per unit charge around charge Q, capital Q, and that, in other words, is known as the electric field strength. So when you're looking at the amount of force that would exist on a small positive test charge around some other charge, we're really looking at the force per unit charge. So that gives us the equation that E, the electric field strength, is equal to F on Q, and that's the equation that's in the data booklet. So the electric field strength is just that force divided by the charge that would be positioned in that electric field, and you can see there from the line above we can identify that that's equal to KQ on R squared. So that would be the situation where we'd have a charge here that's capital Q, and the field would be radiating away from that. And so if we were looking at a point at some distance, so if we had a point here and we wanted to look at how far away that was, and that was distance r, the electric field strength at that point is going to be given by KQ on R squared, or if we were to place charge Q there, it would be the force due to Coulomb's law divided by that charge. That would give us the electric field strength. So I'll just notate over here, E is electric field strength, and hopefully you can see from the quantities that are being used to calculate it, that's going to be measured in newtons per coulomb. F is force and Q is the charge. So F is the electrostatic force in newtons, and Q is the charge, the test charge, in coulombs. So there's all the detail about electric fields. We'll have a look at a few questions and develop that idea a bit further. I'll look at, as I mentioned, one of the PhET apps to hopefully get a better sense of electric fields, how they change, how they're affected by the charge, the distance, and those sorts of things.